6-year-olds out there.
Okay, we're gonna get started. Shh, you're recording right now. Okay, great. Shut up.
We're recording. Y'all choose that language.
Hey, everybody on Zoom. Look, it's just like class.
Hey, Miss Arlington. She's never talked to me.
Hey, Ben.
I don't know why. Why are there so many what? Oh, yeah. Not for long. All right. The figure below displays the basic regression output for the Ford F-150 data from the two statistical software packages, Minitab and JMP. I don't know what that is, but be sure that you can locate the slope, the y-intercept, and the values of S and R squared on both computer outputs. All right, so a lot of times you'll see this Minitab output. So clearly there's S, there's R squared. Everything that you need for your line of best fit or your LSR is found underneath coefficients. The constant is going to be your y-intercept. The other one will be your slope. So that's how you'll know the difference, okay? So your y-intercept comes with constant, so constant coefficient.
What is that like on a calculator?
No, this is stuff that they'll give you. Minitab is a program that they put all the data into, and they give you the little output screen. They don't ever make you do it. All right, and then so here's the other one, JMP. So it says R square right here. That's this value. Then it shows you the root mean square error is the standard deviation of the residual. So that's your S. So this is your S. This is your R squared. Lost another one to remote. Then if you look at the bottom, remember it's your y-intercept is your constant. Okay, so the intercept is right here. And then again, same thing with miles driven, you're gonna have your slope. Okay, so know where to find those. We don't typically use this JMP, but we do use the Minitab. So the Minitab is the one you really need to focus on. All right. So a random sample of 15 high school students was selected from the U.S. Census at School database. The foot length and height of each student in the sample were recorded. Least squares regression was performed on the data. A scatter plot of the, sorry, that's a bad word, with the regression line added. A residual plot in some computer output form of the regression is shown below. So that should say added.
This is recorded.
Because it should have been add, and the D is right next to.
I wish I would. Mom did not like it.
Yeah. Now you can't unsee it. All right, flip through. So here's your two graphs. This is the one that has your prediction line on it. This is the one that's your residual plot. And then we have an output table right here. So it says, what is the equation of the least squares regression line that describes the relationship between foot length and height? Define any variables that you use. So remember that we use the form y hat equals a plus bx. And I told you it's just much easier to go ahead and define your variables within your equation. So that way you don't have to do it twice. So what are we predicting? Look at your, if you look at your chart, this is your X, this is your Y, or your graph, this is your X and your Y. So our prediction is height. So our equation is going to start with predicted height equals, we need our constant or our y-intercept first. So where do you find that on this chart? What did I tell you? Where are you going to look? It is the coefficient, but which one in that column? The constant. This is A. So 103.41 plus. And then your slope is your coefficient with your X value. So our X values are our foot length. So this one is B. So we would do 2.7469. And then our X is actually what? Foot length. Now, again, you can do it where you just put y equals 103.41 plus 2.7469x, but then you have to define your variables. So you're doing twice as much, actually. All right. B, interpret the slope of the regression line. So interpret just means tell what the slope is. So we've already talked about slope. So remember, your slope is your rate of change. So it'll be for every y, for every y. So our slope is 2.7469 for every 2.7469 centimeters of height increase. Foot length increases by 1 centimeter. That'll look exactly the same, or it could be a decrease if it's a negative. So just be careful about that. They're all the same. For every y, how does x change? C says find the correlation. What represents correlation? What letter? How do we find R if they were given all this chart? What do we see in the chart that might help us?
Is that R?
Yeah, this is
That
R
is
squared.
different than the residual, right? Or is it what the residual comes from?
It is.
It is different.
No, it's what the residual comes from. So we're looking for the residual for the correlation, the R, but the R squared is so that we can have the sum of all of them, okay? So the correlation is R, but I have R squared, so how can I find R? Good. So R squared is equal to 0.486. So to find R, we take the square root, and we get R equals, and remember the square root has two solutions, plus or minus 0.697. Why would I have to do plus or minus? What are we looking for? What's the R stand for? Your correlation, right? Can we have a positive correlation? Can we have a negative correlation? Yes. So both of those values are possible. All right. Part D is align an appropriate model to use for this data and explain how you know how. Yes. The residual plot, make sure you mention that. Has no pattern. So that's pretty much what you've learned this unit, okay? So make sure that you understand that. All right, everybody good with this page?
What do you think our correlation is?
It repeats itself soon. So all of this is hard right now because you don't really know it. But then once we get to a certain point, you're doing it again, but you're doing it with two things instead of just
So
one.
do you think this must be the hardest?
Yeah, I think so.
So the R,
Mm-hmm.
that's the thing we learned.
How strong it is.
How
Mhm.
strong, okay, so is it an average of every residual, like distance from
Yes.
the, okay.
All right. This is literally just this top part. There's nothing to add to it. How to calculate the least squares regression line. We have a data on an explanatory variable X and a response variable Y for N individuals. From the data, calculate the means X bar and Y bar and the standard deviations S sub X and S sub Y. That just means do the mean and the standard deviation for both X and Y of the two variables and their correlation R. The least squares regression line is the line Y hat equals A plus BX. This is important. It has been on my test, okay? It has been on my test. I have like 4 different versions of a test. It depends on what I put on there, but this has been on there, okay? So be prepared for this. To find your slope, you do need to remember this formula. B equals R times the standard deviation of Y over the standard deviation of X. remember your slope formula anyway is the change in y over the change in x. You guys know that?
Yeah.
And then we multiply it by the residual. Okay, we multiply by the residual. And then your y-intercept is y hat minus b times x hat. Not y hat, y bar. Thank you. I'm sorry. That's been happening all day. So I thought it's Friday. I'm ready to go home, y'all. There is, honest to God, no writing on the next page. We're just going to read it. Okay. There's no writing. That's why I told it'd go quick. I told you it was going to go quick. I don't know. Depends on how close you get. All right. Putting it all together. Does the age at which a child begins to talk predict a later score on a test of mental ability? A study of the development of young children recorded, the age and months at which each of the 21 children spoke their first word and their Giselle, I guess that's what that is, whatever, adaptive score, the result of an aptitude test taken much later. The data appear in the table below, along with the scatter plot, residual plot, and computer output. Should we use a linear model to predict a child's score from his or her age at first word? If so, how accurate will our prediction be? So it says follow the four-step process. Remember our four-step process: state, plan, do, conclude. Okay. So this is just setting up the problem. I'm gonna flip back and forth between it, but we're gonna go to the next page. You should have do you have a blank page? Yes? Okay. That's what it's for. So we're gonna start with state. Yes, it will take up this whole page. What are we trying to figure out? What was the question that it asked?
If when
Okay. Is a linear model, and I'm going to write big, that's why it takes up the whole page. If you write smaller, it may not be a whole page. Is a linear model appropriate? And then how well does it fit the data? All right, so plan. How are we going to answer the first question? Uh-huh. What will that help us do? Okay, so if no clear pattern, LSR is good or appropriate. And then the one that you probably don't know how to answer is how well does the LSR fit the data? So to answer that second question, we use the standard deviation of the residuals and R squared to measure how well it fits. Okay, and we'll talk about that when we get there, okay? We'll talk about it in a minute. All right, so our do part, you guys look at that residual plot. Tell me what you see. So residual plot has no clear pattern. What about the scatter plot? Tell me about that scatter plot real fast, because they gave you that too. If they give it to you, you might want to use it. What do you see within that scatter plot? Okay, I don't even care about the outliers. Look at it.
Very weak correlation.
Say it again.
Very weak correlation.
Is it?
I think, well, it's clustered.
Okay, but they're close to the line, right? If they're clustered close to the line, that means they're kind of strong. We can also look at this. What's our correlation? What would our R squared be? I mean, our R, what would it be? So this is R squared. So if that's our R squared, what would our R be? I'm sorry, I didn't even mean to use that one. It's adjusted for any kind of discrepancies. No, I'm sorry. It was me. I told you, I've been doing this all day. So R squared is 41.0% or 0.41, right? So what would R be? Does everybody go with 0.64? Is this one going to be positive or negative 0.64 relating to this graph? It'll be negative because it's a negative value. 0.64 is it very strong? Moderately. I would go with moderately strong on this one. So I just wanted to throw that out there just so you guys could see it if they asked about the scatter plot or the R or what it tells you so that you could find this. So I'm going to go this. Scatter plot shows moderately strong, negative correlation. You can put the R on there and that's fine. If you put that calculation on your sheet, they're going to count it as something that you did, okay? If you screw it up, then they're going to mark it wrong. So just be careful. All right, so we did the first part. Now it says use standard deviation of the residuals and R squared to measure how well the LSR fits. All right, so what is our LSR? You guys have to go back and tell me what your LSR is. What's your y-intercept? We just did it on our last example.
Is it 109?
Mm-hmm. Remember, it's the coefficient constant. And then the line below it is our slope. What's our slope?
Negative 1.1370.
And we put an X with that. We asked about the standard deviation, right? What's your S or your standard deviation?
11.023.
If you didn't see that or you don't know where it's from, make a note where that's at, okay, in that chart. It should be clear cut. All right, so what does this mean? This S is 11.0229. What's standard deviation? If I interpret that S, what does it mean?
How much is the average, the typical distance that
Mhm.
a data point has from
So
the-
scores will typically be off by 11.029 when using LSR. So why is this important? Is that a big jump or not? Okay, is that a big deal having 11 points off? Does that make sense? So if we're talking about scores out of 100, 11 points is not that big of a deal. If we're talking about scores out of 30, 11 points is a big deal. Y'all understand what I'm saying? So you also got to look at the context of your problem. So then we're going to talk about R squared. And we said R squared was 41%. What does that mean?
Why are we using R squared?
I'm going to tell you. What is the R squared? Like if I had to interpret it. We did that yesterday.
What's it coming for?
41% of all variation is accounted for by the LSR.
What's different than this and supplementation?
Nothing. We're just using that stuff. Does that make sense?
Yeah.
So this is how we're using this stuff to solve a problem. So yesterday you just learned about the stuff.
Like a formula.
Yeah, now what is this stuff? Now you're like actually applying your,
Gotcha.
okay.
I was wondering.
So then you're at your conclude part. This conclude will tell you why we used what we used, okay? So we did answer the question, is the linear model appropriate? Yes or no?
Yeah.
Why did we find that it was appropriate? There's no clear pattern in the residual. However, why did we use the other two things? That line of fit is going to be off typically by 11 points, but only 41% of data, variation in the data is accounted for. What's the problem with that? It's not a lot, right? So there's still 60, whatever, 60, why can I not do this? 59, sorry y'all. There's still 59% unaccounted for, right? So there's a lot more unaccounted for. So this is what you're going to say. You use those numbers so you can say a linear model is appropriate, but your predictions may not be accurate because only 41% of variation is accounted for. So what this tells you is a linear model is good, just not this one. What if we would have had,
Wait, why would you say this, but it's not good?
it is good. We can use the linear model.
Like,
Just
you mean in
this
other
specific
problems?
equation is not a good
So, like,
linear
would
model.
you ever say the linear model's bad?
Yeah, if you saw a, yes, if you saw a pattern in the residuals.
So like last night on my homework, we were like in straight lines, that was a pattern.
Yes. Is everybody good?
So if the linear model is perfect, then the linear model is good. Or is that not always like that?
No, a linear model is appropriate, but this one is not, this specific one is not. Now, if you would have gotten, instead of 41%, you would have got 80% of the data is accounted for,
Then that would have been bad.
it would be perfect. You would use this linear model and it would be a good fit.
So what if it was only like 20% accountable, then would it be bad?
It's
Or would
still a
you say-
linear model. It's still a linear
Let's
model.
go look at the residual plot.
Because there's no form, we are going to use a linear model. We just aren't going to use this equation because this is not the best equation to use.
So that's saying that you say you need to find
When
a
would you say the linear model is bad?
When you have pattern in the residual.
I'm not even thinking this up.
Yes, you are. You are.
Yeah.
All right. Correlation and regression wisdom. Literally just this part is what we're doing, like this top. So correlation and regression. Are powerful tools for describing relationships between two variables. When you use these tools, you should be aware of their limitations. So we're going to go through the limitations. The first one, the distinction between explanatory and response variables is more important in regression. All right, so here's the thing. Look at your two graphs. One of them has miles driven like we're supposed to in the X, and it has price in the Y. Look at your regression model, predicted price, blah, 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 blah. We've already seen that. But what happens if you switch them, which is completely incorrect, you get a completely wrong equation. That's all it's saying. So you have to know which one is your explanatory and which one is your
It's like
response.
your price will be put in.
Yes, yes, it will be wrong. So already got it? All right. Correlation and regression. If you can't see it, I'll move it in just a minute. Correlation and regression lines describe only linear relationships. Okay, so we're going to look at all of these graphs. We're going to write one more thing on this page, okay? So here's all of your graphs. All have a correlation of 0.186. So we could have good, like the good R value, like 80% of data accounted for or whatever it's going to be. So square this, whatever it is. So the data could be, the variation could be accounted for, but if this is your residual plot, is this a good fit? So it'll be vice versa on our last example. So we'd have a lot of variation accounted for, but LSR may not be a good fit. So it just depends on what they give you to look at. You got to look at the data. So LSR for all of them would have been y hat equals 3 plus 0.5x. But that doesn't mean that that line is a good fit for every single one of these data. Does that make sense? They're not. I'm just telling you what they are. So this is what they're showing you, is that all four of these graphs have a R of 0.816, and they have the y, their y hat or their prediction line is 3 plus 0.05x. But look at all the variation that you're going to have in certain ones of these.
I don't know, if those all have the same, LSR and the same R line, how they all look different?
Because they all can. Because it doesn't matter, like where you put them. So think about different, I don't know how to explain it really good. Different numbers can give you the same mean. Does that make sense?
Okay.
So different, I don't know to give you a specific
That
example, but
actually
you,
makes a lot of
so
sense.
all of these could have the same mean value. They
That's
could
like
have the,
completely different data sets.
yes,
Okay, so
yeah.
they're not all the same set.
Correct. They're different sets of data. Yes.
Okay, this doesn't have any relationship, but like with A, would that be considered a pattern?
These are not residual plots.
Yeah.
These are not right now.
Oh, okay.
But if it were a residual plot, then no, I would not say that that one is a pattern. This one would be a pattern. Sorry, y'all. All right. Number 3, correlation. And least squares regression. Lines are not resistant. And we know that. If we throw an outlier out there or something way to the end, it's going to pull that line away from where it's at. It's going to make it move. Okay. So what it's showing you in those graphs is this child 19 will pull that correlation line. If we take that 19 out, it'll make that correlation line stronger. So outliers make them weaker. See where I got it? All right, last page. I told you, look, do this quick. Last page. So outliers and influential observations in regression. So that's what all this chart is showing you with and without child 18 and 19. So an outlier is an observation that lies outside of the overall pattern. Points that are outliers in the Y direction, but not the X direction of a scatter plot have large residuals. Other outliers may not. So in the Y direction means up and down. So this would be child 19 on the chart because he's a lot higher than everybody else. It's up instead of to the left or right. So an observation is influential. For a statistical calculation, if removing it would markedly change the result of the calculation. Points that are outliers in the x direction of a scatter plot are often influential for the least squares regression line. So that's all that chart is showing you. So I have child 19 here. With child 19, it's going to be the one in the middle, but without it, it's going to pull it back down towards everything else. So you see it pulls it towards child 19. Does everybody see that? Same thing with 18. It'll do that as well. Then number 4, and there's a little bit of writing after this. Association does not imply causation. So this is what you need to know. An association between X and Y even if it's strong, is not by itself good evidence that changes in X actually cause changes in Y. So there are more things that we need to know and we need to understand. Sorry, I'll try to make it a little bit bigger so you guys can see it. All right, so that'll finish up our chapter 3. Is everybody good with that? Monday and Tuesday will both be review days. Monday will probably be more of a work day for you guys. Tuesday will be a review with me, and then Wednesday will be your test. Okay, you got it? You need to work hard on this test. It'll be the last test that we get in this grading period. Don't freak out, okay? And then make sure that anything else that you haven't done, you need to get that done. Okay, so any zeros that you have need to be fixed. So everybody good? All right, so remember that your homework tonight, I'm gonna stop sharing and stop recording for a minute.